So we are going to continue 1-6, talking about limits. We've already talked about this when we discussed the definition of a limit. This is nothing new. The notation that if and only if means that this has to be true, and if it is, it implies this. If this happens to be true, then it implies that. So you can go backwards. This just says that the limit exists if and only if the left side and the right side match. That's all that notation means. It's hard to see, but there is that little negative meaning approaching from the left and the little positive meaning approaching from the right. So that is just something that we've discussed. That's a formal way to write that very thing, that both the left-hand side and the right-hand side have to match. They would both be L. If they're L, then that's the limit as we approach A. Now that even works for our approaching an asymptote. Both sides have to go up to infinity, and that would be your answer. Both sides will go down to negative infinity, and that would be your answer, okay? So let's talk about examples 7 and 8. Last year, I mentioned to you that the absolute value of a function is a piecewise function. And I told you, you might recall when we were studying parent functions, I mentioned how you would get a little bonus point if you told me the piecewise function portion of it. So the first thing I want to do for 7 is I want to rewrite the absolute value as a piecewise function. So please rewrite that as the opposite of x when x is less than 0, and positive x when x is greater than or equal to 0. And that's what makes our v. That is a really bad v. Okay? So because this side of the graph is a slope with -1, and this side of the graph is a slope with +1. Now, what we're trying to show is that the limit as we approach 0 of our function is equal to 0. And instinctually, we can see both sides of the graph are heading to 0, but this is why. So let's look at the limit from the left and the limit from the right. Let's approach it from both ways. From the left, we know that that side of the graph, because of the piecewise function, is heading to a height of 0. This side of the graph is heading to a height of 0. Since they match, the answer is 0. Bam, that's it. And you know, if you know the graph of it, a graphical interpretation is also a way to kind of show that. Now, in mathematics, the higher you get, proofs do come back, but they're different. They're not those 2-column proofs you see in geometry. Many times they're algebraic-based proofs, and more of, okay, I have a definition that says if the left side and the right side match, then I know for sure that's the limit. And then that's the kind of thing that we see here. Okay, so that's really all we have to do for 7. But 8 is actually a very, very neat one in the fact that by manipulating that absolute value equation just a little bit, we mess it up. Okay, so let's go over now and let's call our function the absolute value of x over x. Now we're still going to rewrite it as a piecewise function. So what we get is that it's -x over x when x is less than 0. And it's positive x over x when x is greater than or equal to 0, reliant upon the definition of an absolute value. We just took the absolute value part and rewrote it based upon the fact if it's negative, it flips, becomes the opposite. And if it's positive, it doesn't change at all. Okay? But those things reduce a little bit. The opposite of -x, or the opposite of x gave us that -x, and when we divide by x, we get -1. And on the bottom, we didn't change the x, so x divided by x is positive 1. Okay. So if we were to graph this function, on the left side, we are an open circle and a horizontal line at a height of -1 until we hit 0. And then this one is where they include the equal to. And so we have a closed-in dot, and then we have a graph that looks like that. Okay. So let's use the same exact thinking we did before to show that it does not exist. So the limit as we approach 0 from the left, and the limit as we approach 0 from the right. Let's see what we get. Well, our left-sided limit uses that bottom function. We can see that here, anything to the left of 0, and it is approaching a height of -1. This one, as we approach it from the right, is heading to a height of +1. They don't match. So the limit as x approaches 0 of f does not exist. That's the power of that if and only if statement. Is if they don't match, we know the limit doesn't exist. So if we can definitely show that they don't match, we get instantly that the limit doesn't exist. So watch out for absolute values. I would suggest to you as we do limits, and eventually when we do something called a derivative, you're going to have to rewrite them as piecewise functions every time. So, just keep that in mind as we go through the process. If they ask you about an absolute value, rewrite it and see what happens. Do we have any questions about example 7 or 8? Okay. Let's look at example 9. Now again, we have an issue about a piecewise function. We want to rely on the algebraic possibilities as much as possible because graphing can be funky, okay? Now I'll show you the graph, but let's talk about it algebraically. So we want to find the limit as x approaches 3. So let's do the limit as x approaches 3 from the left, and let's do the limit as x approaches 3 from the right. Now we only have to do that if 3 is our border value, because the border value is going to determine if the switchover, if the graphs line up and match together. If the value is just like, if we just pick 2, oh, you can put the f of x or not. I was just being lazy. They just wrote an f, so I was like, I'm just gonna write an f. No, we can, yeah, you can or cannot. It doesn't matter. Okay, so if we chose a value like 2, we just get to use that function. If we choose a value like 7, we just get to use that function. And those are polynomials, and we can just use direct substitution. But because it's a border value, we have to check the border, are we coming in, one graph isn't touching the other graph, and that would tell us that the pieces match up. Okay, so for the this notation here, that left side, that's numbers that are less than 3, so we're going to use this function. So let's try direct substitution there. So if we plug in 3, we get 2 squared minus 5, or 4 minus 5, which is -1. Now, for this notation, we are coming in from the right, so we're going to be using values that are bigger than 3. So we can use direct substitution into that function, and so we get 6 minus 7, or +1. Since they are different. Oh, 6 minus 7 is negative 1. I'm so sorry. I guess they do match. Can't do math today, sorry about that. Anyway, since they match, the limit as x approaches 3 of f of x is equal to that value of negative 1.
So that bottom equation is x is if x is greater than or equal to 3?
It doesn't matter if it's equal to or not, because remember the limit is as we are approaching it. So even if we plugged in a number like, let's say, just think of to the right of 3, like if we plug in 3.00001, we are going to be super, super, super close to negative 1. So you can use direct substitution because they are asking where are you heading, if not necessarily where you land. So we're heading toward negative 1. We're almost at negative 1. We're super, super close to negative 1. So think of it like that. Any other questions about example 9? Yeah, that's one thing you have to really wrap your head around about limits. It's not necessarily where you land, it's where you were heading, where you wanted to go, not necessarily where you ended up. We good with example 9? So I think what examples 7, 8, and 9 we're trying to remind you of is piecewise functions. The border can have issues. So you got to really check the border values. If it's any other value, you just get to plug it in and it's going to work. But that border, do they match up? And you can even put them in Desmos, see if they match up. Okay. And that leads us to a very important theorem that we're barely going to use, but it's neat. It's called the squeeze theorem. We're going to start out with this part of things. So let's just talk about that. If two functions are always related in such a way that f of x is always less than or equal to g of x, then the limits as we approach any a that is in the domain of both, the limit of f would be the limit of g. Now let's think about why. Okay, I'm going to draw a little picture. It's not going to be pretty, but it should help you. Let's say our g of function is up here. And then let's say our f of function is here. Whatever a value we pick, won't the thing we are approaching for g always be higher than the number we're approaching for f? So it's about a height, and so if the f of x is always under or less than the g of x, then the g of x will always be less than or equal to, or I'm sorry, the f of x will always be less than or equal to the g of x. That's all that's saying. And then that gives us the squeeze theorem, but you have to have g of x stuck between f and h. And what this says is if the h function is the top function, and then the f function is the bottom function, and they both are going to some limit L. And if the g function is stuck in between there, it also can go to L. Okay? So look again. If h is the top function, it has to be always higher or equal to the others. F is the bottom function. It's always lower than or equal to the others. And if g is squeezed in between there, if this one's going to L and this one's going to L, then g is stuck in there and it's going to go to L as well. That's all that's saying. Okay? It must be squeezed in there in between. Now, why do we care? Well, we care if g is a function. Let's say when we try to do direct substitution, it doesn't make sense. It's hard to tell what's happening at that value. But this is like, say, a nice polynomial, and this is like a nice polynomial, and direct substitution works for both of those, and we get a limit of 5 for both of those. Then we're forced to know that the limit at that spot is also 5 there. So it's just a way for us to take a complicated function where we don't know the limit, and we can use two functions that we do know the limit, and we can use it to help us. That's all that means, okay? So we're never really going to use the squeeze limit much, the squeeze theorem much, but I wanted to show it to you. It's just kind of interesting. Okay, so that leads us to this example. If I ask you to find the limit of that x squared times sine of 1 over x, if you were to put 0 into that function, it is undefined. Algebraically, we don't have a nice way to manipulate the sine of 1 over x. So you look at it and go, I have no idea. So what we're going to do is we are going to, well, we're going to fix it a little bit. We're going to manipulate what we know. Okay, so let's think about this for a minute. Would you agree that the sine of anything is always stuck between positive 1 and negative 1? We know that about the sine function. It is always stuck between positive 1 and negative 1. Now, that's the one thing we know. So would you also agree that the sine of 1 over x also is somewhere between positive 1 and negative 1? Okay. Now, one of the things you learned about inequalities is if you multiply by a positive, it doesn't change the symbols, right? If you multiply by a negative, it'll change the symbols. But let's multiply this entire thing through by something we always know is positive. Let's multiply it through by x squared. When we do that, we get negative x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to positive x squared. That's the function we were looking for. So what we have done is we have found two functions that are squeezing the function we're looking for. That's a polynomial, right? That's great. That's a polynomial, right? That's great. We can use direct substitution on those. So let's find the limit as x approaches 0 of negative x squared. Let's find the limit as x approaches 0 of positive x squared. And that is not written right. There we go. That's better. And let's see what happens. By direct substitution, this is 0. This is 0. So that's telling us that the limit as x approaches 0 of x squared sine of 1 over x, since it's between 0 and 0, what's the only number that's between 0 and also between 0 and 0? 0. So we know that that has to equal 0. So it's just kind of an interesting result. We're just thinking about some things we know about the sine or the cosine. So that would be true about a cosine as well. Any cosine function is stuck between negative 1 and positive 1. You get kind of a squeeze going on because of it. Now, if you used x sine of 1 over x, it wouldn't work because it is x positive or negative, and that could mess things up. But because we're multiplying through by a positive, that x squared, it works. So that's showing algebraically. So that's in a way an algebraic proof. So I always loved algebraic proofs more than geometry proofs. When I got my degree, my master's degree in math, you got to do a lot of proofs, but they're more kind of like this. But here's where the geometry thinking, when you were back in like 9th or 10th grade, I would have to, when I multiplied by x squared, I would have to say, since it is a positive value, you have to put in words why you can do that. So that's the only difference. I didn't show you all those things. I said those things, but I didn't show up to it. Okay, so this is your 1/6 assignment found in your book. Please work on the odds 1 to 31 and 47. So you have 2 assignments that I believe are due on Sunday. So if you could take this weekend, work on those, and if you're stuck on anything, please let me know.